right, we're going to take a look at the beginning of chapter 6, which starts trigonometry. So what I want to do first is just kind of look at the word trigonometry, break it down, and see if we can kind of figure out what it means. All right. So let me go like this. All right, when you look at the word, does anybody notice like a prefix or a suffix or part of that we can kind of figure out maybe what that part means and then figure out what the rest of it means? Michael?
Try.
Try? Yeah, what does that mean? 3. So try means 3. And how about gone? We see that with, there's a lot of words in math that end in gone.
Octagon.
Like octagon.
It's a shape.
It's a shape, right? So if something ends in gone, it means it's a shape. Specifically, it's a two-dimensional shape, right? So it's a shape with sides, a gone, right? Octagon, hexagon, pentagon. There's a name for every two-dimensional shape that ends in gone. We don't always use it. Like for a four-sided shape, we call it a quadrilateral, but you could call it a tetragon, right? Tetra, that means 4. That's why Tetris, if you've ever played that game, all the shapes in the game have 4 blocks, tetra. Three-sided shape, we normally call it what? We don't normally call it a trigon, we call it triangle. But trigon is another word for a triangle. So three-sided shape, which is really just triangles. And then the word metri. Does anyone know what metri means?
Measurement.
Yeah, it means measurement. So we see that in a bunch of different subjects like trigonometry, geometry. That's it, all I can think of. But metri anyway means measurement, and triangle measurement. So pretty much everything that we do in trig can be related to a triangle. Let me show you a very simple example of something. Let's say you had a tower that's perpendicular to the ground. So this symbol means 90-degree angle. Right? And you're standing over here. And you want to figure out something. Let's do the height. Right? Well, if you want to know the height, one thing you'd have to be able to figure out is the angle from where you are to the top of the tower. That's actually not that hard to figure out. They have equipment you can do it with, like if you had like a scope or you had some kind of like a transit. Anyone ever see like on the side of the road? Sometimes you see a tripod set up, and then like further down the road another tripod. Usually they're like there's a laser on one of them, and they're shooting it into the other one. And they can measure like how far away something is. Maybe they're measuring like property lines or something like that. But anyway, there are devices to figure out the angle. So we could get the angle to the top of the tower. We could figure out how far we're standing from the tower. As long as there's nothing between us and the tower. If there's like a ravine or something, then we can't do it. But if it's just flat ground, that's easy. We just measure the distance straight to the tower, and we could figure out the height of this building because we just created a triangle right there. So there's your triangle, and basically finding the height of that triangle is the height of the building. There's other ways to do it too. If you've geometry, you might have looked at like shadows and proportions. Like if you know how tall you are and you know the length of your shadow, and you can see the length of the shadow on the building, then you can figure out how tall the building is. But this is another way that uses the trig. Now, this isn't too bad because it's a right angle. Right? Sometimes things are built and they're not straight. So like if this was like the Leaning Tower of Pisa, it would be a little crooked. It would make a right angle with the ground. Then it gets a little harder to figure out. And we can still do it, but it's a little different. So all kinds of things we'll talk about with trig. Has anyone heard of like triangulation? What it means to triangulate somebody's position? Yeah, it basically means you're figuring out where someone or something is. So as an example, let's say you had land. So this is all land. On this side is water. There's a boat out there. And you're trying to figure out where the boat is, right? You don't have any way to communicate with the boat, but maybe the boat has a light on it. And you can see the light, right? You see the light. And to keep it simple, pretend the boat's just anchored. It's not moving. Well, if you're standing here and you can see the boat, the problem is you might be able to see it. Maybe if it's at night, you can see the light on it. But you can't tell if it's 5 miles, 6 miles, 10 miles. You can't really tell how far away it is. But you could see it. And you could say, well, the boat's that way. I see the light. Well, if somebody else was standing over here, and they do the same thing, and they say, you know what, I can see it, there's a light that way. If those two people coordinate with each other, they can figure out exactly where the boat is, because they're seeing the same thing, not moving, from different perspectives. Maybe they know how far apart they are, or this guy could say, oh yeah, I'm on this street, and I'm over here on this street. And we can say, oh yeah, we look at a map and figure out how far apart we are. And what you've done is you just created a triangle right here. And you can figure out exactly where the boat is. You triangulated the boat's position. But you need 2 people to do it. Or you could do the same thing. If the boat's not moving, you could go here and then drive to another spot and look at the boat from over there. If the boat's moving, that kind of complicates it. Right? You can do the same thing with like a cell phone, depending on like cell phone reception and the strength that the phone gets from the tower. They can figure out based on what tower you're connected to, because they know where the tower is, how strong the signal is. And maybe if you're in range of a couple towers, like let's say this is a tower, cell phone tower here, another one here, and another one here. Maybe this one sends out signal like that, this one like that, and this one signal like that. Well, if you're picking up signal from the top 2 towers, and you can figure it out because if you actually look at it, you can kind of figure out what tower you're connected to. There's like a special app for it. But if you're connected or in range of 2 towers at the same time, they can kind of figure out, well, they must be in that area, because that's the only area that you can pick up both towers at the same time. Right? So again, a little more with triangulating and finding out where somebody is. And that's how GPS works. It triangulates your position, but usually GPS uses more than 2 satellites. You usually need a minimum of 3 or 4. Like if you've got a GPS in your car, sometimes it says like acquiring signal, and when it only has 2, it's not enough. But once you get 3 or 4, it can figure out exactly where you are using trig. So we don't really get into anything as fancy as how GPS works, but we'll do kind of some of the basic problems I showed you earlier later on. So first thing we're going to look at that we use a lot in trig are angles. So I'm going to start just by defining what an angle is. So an angle is made up of 2 rays. Each ray has a vertex. And what makes it an angle is we put the 2 vertices at a common point, common starting point. So there's a ray, just all by itself. Here's another ray. And now when I move them so that they have the same common starting point, now we've created an angle. So when you draw an angle all by itself, it's always drawn as 2 rays. When you draw it in a shape, like if I go back to the picture I have on the other page, these 3 things that I'm numbering 1, 2, and 3, those are angles, even though they're not made up of rays, they're made up of line segments. So usually in a polygon, an angle is where 2 line segments meet. Okay? When you draw it all by itself, that's when you use rays. So when you have the rays, you get two sides. You've got this side, it's kind of pointing down, and then this side is pointing up to the right a little bit. Well, one side is called the initial side, the other side is the terminal side. If we're dealing with positive angles, you always move in a counterclockwise direction from the initial to the terminal. So where you end is the terminal side. I just think of terminal, it's the end, right? I think I have a picture right here. So I've labeled the initial side and the terminal side. So it says for positive angles, you move in a counterclockwise direction between the two rays, not on the outside. Okay, because technically you have two angles here. You've got the one on the outside and then the one on the inside. So when I say I'm talking about inside, so you start at one side, start going counterclockwise till you hit another side. Where you end is the terminal side. Okay, so if I go back up and look at the angle that I drew, I could do the same thing. Start at one side and rotate counterclockwise. This would be your initial, and this is your terminal. Counterclockwise between the two rays. Okay. Any questions on that? We're going to make it easier to figure out which side is initial and terminal. This is not how you would normally draw an angle. There's a little bit nicer way to position it. This one's actually a little crooked. This one's very crooked. It's like it's been turned. It shouldn't look that way. Okay, and I'll show you that in a few minutes. All right, so when we name angles, okay, we have to give them a name. We have to give them a letter. Well, in algebra, a letter you use a lot is like X. When you don't know a number, you say it's X. When we don't know an angle, a lot of times we use a Greek letter. Depending on the context of the problem, some letters are more common, like when you're graphing. X is common for like a horizontal axis, and Y is common for vertical. Well, there's going to be certain times we'll use certain Greek letters. So I'm just going to go through the names of these 5 Greek letters. The first one is the first letter in the Greek alphabet. And does anybody know what that one is? Sam?
Alpha.
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 Yep. Alpha. All right. The next one looks kind of like a B, but one side is a little longer. And that's the second letter in the Greek alphabet. And again, these are both lowercase. Does anyone know what the one that looks like a B is?
Beta.
Yep, that's beta. The capital beta in the Greek alphabet actually looks, I'm pretty sure it looks just like RB. And the capital alpha, pretty sure it looks like R capital A. I'd have to double check to be sure. All right, this one looks kind of like a Y, but it's like a little curve on one side. Does anyone know what that Greek letter is? Rhymes with grandma? It's gamma. Gamma. All right, so gamma, that's usually when alpha, beta, and gamma are all used together in a certain type of problem. These would probably be used in the problem I showed you about the boat in the ocean and you see a light on it. That's probably how you would label the angles you don't know. How about this one? Circle with a line in the middle?
Theta.
Theta. That one's very common. Okay, that one we use pretty much anytime you just have a single angle by itself and you don't know what it is, let's call it theta. Alpha, beta, and gamma, those are used more when you have a set of 3 angles, usually in a triangle that you don't know. And this last one, looks kind of like a W, but the sides are curved a little bit. Does anyone know what that is? It's the lowercase version of this. That's omega. That's a capital omega at the top. That's a lowercase omega. Okay, again, we're not going to use all those today, but if you ever see those Greek letters come up, now you know what they're called. I think you're going to see theta later on today. So, I told you there was a way we can draw an angle that makes it easier to figure out what side is the initial and what side is the terminal. And the way you draw it is what's called standard position. Okay, so if you draw an angle in standard position, that's when two things happen. One, you put the initial side on the positive x-axis. And the second thing is you put the vertex at the origin. So if you had a set of axes, that's what an angle looks like in standard position. Initial side on the positive x-axis, terminal side at the origin. Now, what if I did that? Is that still standard position? No, what's wrong with it?
It's not at the origin.
Right, the vertex isn't at the origin. The initial side is still good. That's where you want to put it. But vertex isn't at the origin. All right, what if I did something like this? How about now? Is that standard position? No, what's wrong with it now?
The initial side isn't on the x-axis.
Yep, the initial side is not on the positive x-axis. The terminal side is on the y-axis. But the definition of standard position has nothing to do with where the terminal side is. Okay? So that's standard position. I also have a program that lets me draw angles in standard position. Okay? I can't move the initial side. And I can't move the vertex. All I can do is put the terminal side in different spots. But if you look at the two black segments, which again, they should be raised, but that's fine. If you look at the two black segments, that's what's forming your angles. You might notice that there's two numbers, 206 with a little circle up higher, and then 3.6. Does anyone know what the top one is? What that little circle means?
The degree of the angle.
Yep, that's measuring an angle in degrees. We'll look at more tomorrow. And then the bottom one doesn't have a label. When it doesn't have a label, there is a label. It's invisible, and it means something. Does anyone know what that one is?
Radians.
It's in radians. So we're going to talk more about what it means to measure an angle in degrees and radians, but I don't think we're going to get to that today. We'll see. Oh, actually, we might. We might get to degrees and radians. We'll see. So, degrees is one way to measure an angle. If you made one full rotation, all right, so if I bring the program back up, if I drag the terminal side all the way back around, how many degrees would it be? Yeah, as long as I position it, it would be 360 degrees. All right. So one complete rotation, and that was, I went counterclockwise. It was 360. What if you did a half counterclockwise revolution? How much would that be? Chuck?
180.
That would be 180. How about if you did a quarter revolution? 90. Now, notice I specified a direction, clockwise, or counterclockwise, counterclockwise, counterclockwise. They're all positive. What do you think would happen if I went the other way? If I went clockwise? What would happen?
We can have negative degrees.
Well, it doesn't really make sense when you draw a triangle. So like if you make a triangle on paper, all the angles are positive. But in trig, you can have negative angles. So that's what would happen here. Right? You would get negative angles if you go the other way. Right? And again, I don't really think of it as a negative angle. I just think of it as an angle going the other way. So the negative is just there to tell you, oh, go the other way from the normal way you go. So negative angles happen when you rotate clockwise. And that's what I write right here. So counterclockwise direction, positive. Angles measured in the clockwise direction are negative. Now, an angle can also be even larger than 360. All that would mean is you've gone around. Yeah, you've gone around more than one time. So I'm going to show you two angles, and depending on how you draw it, and you show them somebody the two angles I'm about to show you, they wouldn't be able to tell the difference between them. Let's go like that. So in that picture, the initial side is on the positive x-axis, the terminal side is on the y-axis, positive y-axis. That's a 90-degree angle. Now, if I did this, how does the, oh, it's close, I just can't get it right on. How does the initial side compare now to where it was before? It's in the same spot. How does the terminal side compare now to where it was before?
1 1/4.
Okay, so where is it now and where was it before? It's in the same place, right? It's straight up on the positive y-axis. So if you didn't have that little red spiral in there and you didn't see the numbers, couldn't tell, what was going on, you wouldn't be able to tell the difference between the 90 and 450. They have the same initial and the same terminal sides. We can put that little spiral in, and usually I would put an arrow on the end so you know which way you went, but that'd be the only way to tell the difference. So here's another example. 360. Initial side and terminal side are right on top of each other. Okay? Can't even tell them apart. If I go to 0, same situation. Initial and terminal side are right on top of each other. These two angles have a special name. When the initial and terminal sides are right on top of each other, those are called coterminal angles. So, coterminal angles mean they have the same initial and terminal sides. So I want to think about how we could find coterminal angles. We already know a couple examples. I did 90 and 450. 90 and 450 both looked like right angles. What arithmetic could you do to change 90 to 450? What do you think you could do? Like if you didn't have that picture to see it, how could you just do it with numbers? Yeah? Square it? What do you mean?
Like multiply by itself.
Well, if you did 90 times 90, that would be 3,600.
Oh, maybe not.
So, a good guess.
Multiply by 2. No, just kidding. I'll say.
Yeah?
Add 360.
Yeah. If you add or subtract 360 degrees, you will always get another angle that is coterminal with the one you started with. So if I go to 45, right there, if I add 360, I get 405. And it's exactly, the initial and terminal sides are in the same spot. So we use that trick if we get angles that are too big to kind of think about, like 863 degrees, kind of a big number, hard to wrap your head around it. Well, if you subtract 360 once, and then do it a second time, you can find an equivalent spot, a coterminal angle, that's smaller. And then smaller numbers are easier to work with. Now, that's examples of subtracting 360. I had an angle that was too big, So I subtracted 360 to make it smaller. When might you want to make an angle bigger? Yeah, if you have a negative angle, like this, and you're like negative 507. Not sure where that would be. Well, if you add 360, and then add it again, most people have an easier time thinking about a number like that, because it's not negative. All right. So that's what we'll practice next. So I'm going to give you an angle. I'm going to ask you to make a sketch and then find an angle that's coterminal and positive, coterminal and negative. Now, it's just a sketch. You don't have to get out your protractor and make it perfect. Just roughly. Right. Let's start with 30-degree angle. So where is the terminal side going to be for a 30-degree angle? Like what? We'll just start with what quadrant is it going to be in? Oh, no.
Is it the second quadrant?
So second one over here?
I'm sorry, the upper right hand.
Upper right. Yep, so it's quadrant 1. Now, I want to try to put it somewhat accurately in quadrant 1. So this is 0. This is 90. Where's 30? Kind of, if you compare 30 to 0 and 90, where would it be? In the middle? Well, 45 would be right in the middle. It would be exactly in the middle. A little bit what? A little less. So it's like a third of the way. So 30 is a third of 90. So just try to make it look like it's a little less than half. That's good enough. So there's my terminal. And there's my initial. Now they want us to find two coterminal angles. One positive, one negative. All right. Sam, what would I add to 30 degrees to find a coterminal angle that's positive?
360.
Yep, we'd add 360, and 360 plus 30 is 390. All right, now let's find a coterminal angle that's negative. Okay, so what would I do with 30 to get a coterminal angle that's negative? Okay,
Subtract 360.
subtract 360. And what's 30 minus 360? Sorry?
Negative 390.
Yep, negative 330. That's it. So you found a positive and negative coterminal angle. All right, let's do 145. Okay, what quadrant is the terminal side going to end up in this time? Okay.
2.
Yep, it's going to end up in quadrant 2. If you go right to the edge of quadrant 2 on the bigger side, it's 180. On the smaller end, it's 90. So now I want to figure out where 145 would be. It's either closer to 90, closer to 180, or right in the middle.
A little closer than 180.
It's a little closer to 180. 135 is right in the middle. That's 45 away from both. 145 is a little bit over half. So if that's half, like the best I can do, we're going to go a little less than half. So there's your angle right there. You can put the arrow if you want to show the direction. I didn't do it on the first one, but you can. Okay, so there's our angle. And what's the number that we use to find coterminal angles? We add or subtract 360. So let's take 145 plus 360, we get 505. Take 145 minus 360, and we get negative 215. If I had to work with that angle, I would have just left it the way it was. 145 is probably the easiest way to work with it. Usually 0 to 360 is what you're shooting for. Not too big, not negative, just 0 to 360 is good. do this one, negative 45. All right, so this time, initial side, well, doesn't change. Which way am I going to rotate to get to the terminal side this time? Clockwise. And we're going to go clockwise 45 degrees. If you go 45 degrees, how far through a quadrant do you go? Halfway. Right? You go exactly halfway. So there's your angle. Okay, let's see. If we add 360 to that, what would that give me for a coterminal positive angle? Yep. 315. And if I subtract 360 from that, what would that give me for a negative coterminal angle? Yeah.
Negative 405.
Yes, negative 405. Okay, just a little practice finding coterminal angles and some basic sketches. Questions on those? All right, let's look at some more definitions. So I'm going to use the Greek letter theta in the following definitions. And theta represents an angle. What's an acute angle? It has to be between two things. Yeah?
Is it an angle less than 90 degrees?
It's less than 90, but more than 0. A lot of people just say the less than 90, and then I come back with like, well, how about negative 10? Negative 10 is not an acute angle. It has to be between 0 and 90. What about right angle? Is it all? What's a right angle? It's exactly 90. So this one is not a range, it's exactly 90. How about if we get bigger than 90? What do we call that kind of angle? Obtuse, but it still has to be less than 180. If you get bigger than 180, that's called a reflex angle. Not sure if there's an upper limit on that. I would think it would be 360 for the upper limit. I'm not sure. But those are the ones you need to know. Now, those definitions apply to a single angle. Complementary applies to two angles. Two angles together add up to something. Does anyone remember from geometry what complementary angles add up to? Yeah?
Angles that add up to 90 degrees?
Yep. Two angles that add up to 90, and they have to be positive. So if you said negative 10 and 100, I'd say no. Yes, negative 10 plus 100 is 90. But they're not both positive. So two positive angles that add up to 90. And does anyone know the other one you usually study with complementary? Yeah?
Is it supplementary?
Supplementary. And what do those add up to?
180.
They add up to 180, and both the angles have to be positive. So you can't say like 190 and negative 10. No. So supplementary, two positive angles that add up to 180. So the only case you could have for supplementary is you either have two right angles, two 90s would make 180, or an acute and an obtuse angle. You couldn't have two obtuse angles, that'd be too big. And you couldn't have two acute angles, that'd be too small. So you could have one of each or two 90s. Negative angles don't have complements or supplements. So if I said, what is the complement of negative 15 degrees? That means what angle would you add to negative 15 to get 90? There is none. Negative angles, it's just a definition. You don't have complementary or supplementary with negatives. Okay, so here's some examples, and we'll just find the complement and the supplement. Okay, what's the complement of 48 degrees? Forty-two. Yeah, 42. How about the supplement? $132, yeah. You just take 180 minus 48, you get 132. So C is complement, S is supplement. How about, Rebecca, what's the complement of negative 18?
There isn't one.
There isn't one. There is no complement. So you could write doesn't apply or not applicable, whatever. How about the supplement? Same thing. Are no complements and supplements for negative angles. Now, how about x degrees? Now, you've got to assume x isn't negative, because if x was a negative angle, you couldn't do it. And if it's a complement, we have to assume that x is less than 90. Because if I said, what's the complement of 112 degrees? Well, that's too big. So pretend x is an angle less than 90, but greater than 0. Yeah.
Oh, what?
Oh, do you know what the complement would be?
I mean, x plus another number equals 90.
Okay, let's start with that. X plus another number equals 90. Now solve for another number. How would you get another number? Or how would you get, I'm sorry, how would you get x by itself? I want to move another number to the other side.
X plus 90 minus that other number.
Well, let's start with that. So x equals,
Or x, yeah, x equals 90 minus that other number.
yeah, 90 minus the other number. So the complement, in this case, is 90 minus our angle. 90 minus the angle. So if the angle was 10, the complement is 90 minus 10. Right? How about the supplement? It would be the supplement of x degrees. And again, assume x is an acute, a right, or obtuse angle. Couldn't be bigger than 180, couldn't be negative, it wouldn't work.
180 minus x.
Yep. 180 minus x. So there's your supplement. Questions on complements and supplements? Okay. So, last thing we're going to look at is converting between what's called radians and degrees. So radians is another way to measure an angle. If you take calculus, radians is the more common way to measure angles. Degrees isn't really used. So, I'm going to show you a picture first. This is kind of something you can visualize to see what a radian would look like size-wise. Okay? There's not really going to be any numbers in this. Just going to be, well, it's not going to be any conversions. We're not changing between degrees and radians yet. So what I've drawn here is what's called a central angle. A central angle is just an angle in a circle where the vertex of the angle is right at the center. And then there's two rays. I have ray CB, which hits the edge of the circle right there, and ray CA, which hits the edge of the circle right there. Now, what I've done is I connected point A to point B, tracing along the perimeter of the circle. That's called an arc. Arc AB or arc BA. Arcs are non-directional. Doesn't matter which way you say it. Okay. Any question on that picture? Now, let me show you what 1 radian would look like. So angle ACB would be exactly 1 radian if the following happened. If you measured the length of this arc in red, so like say you took a piece of string, you put it on that arc, got the length of it, straightened it out, and then put it on a ruler, and you measured the length of the arc. And then you measured the length of that radius. Ray C or CB and CA are the same. They're both radii from the same circle. Well, if the length of the radius and the length of the arc came out exactly the same, then you would have a picture of 1 radian. So if the length of the arc comes out exactly the same as the radius in the circle, then this would be 1 radian. That's actually a little big. It's not quite to scale. I think the arc is bigger than the radius there by a little bit. So that's a little bigger than 1 radian would really be. Okay, but that's something you can kind of visualize. All right? If the arc is bigger than the radius, then you would have an angle bigger than 1 radian. If the arc was smaller than the radius, let's say you drew it like that, and then your arc was only from here to here. If that arc is smaller than the radius, then the angle is smaller than 1 radian. Any question on what a radian looks like visually? The connection between the length of the arc and the radius. Okay. So now we're going to look at how do we convert between degrees and radians. Well, anytime that you want to convert between 2 units, you have to already know at least one connection between the 2 units you're trying to convert. So let's say I wanted to convert feet to inches. Can anybody give me a connection between a certain number of feet and a certain number of inches? Yeah?
1 foot equals 12 inches.
1 foot equals 12 inches. How do you know that? You just know, right? There's just some facts, you learned them really early on, you just know that in 1 foot there is 12 inches. Now, somebody else could give me any other number you want. You could give me a number in feet, you could give me a number in inches, it doesn't matter. And I could convert it using the fact that he gave me. But the key is I can put any number I want. Like let's say, I don't know, somebody pick any random number of inches.
72.
72. So if I put 72 in the bottom, I can solve for x in the top just by cross multiplying. But the key is I had to already know something to start with. If I don't know that, then I'm stuck. So when we convert between degrees and radians, you already have to know something to start with. And that's what I'm going to show you. And the fact that you're going to have to know to already start with has to do with what's called a unit circle. A unit circle is just a circle with a radius of 1. That's all it is. Just a special circle, and the radius is 1. Now, I don't have to do this with a unit circle. I could do this with bigger circles or smaller circles. I chose to use 1 for the same reason Jake probably told to give me a 1 right there. I could have said in 2 feet is 24 inches. I mean, it's not that much harder to work with that. But he gave me the simplest fraction he could. It had a 1 in it. So that's why we're going to try to do something based off having a circle with radius of 1. It's somewhat simpler. All right. So in a unit circle, something special happens. This only happens in a unit circle. Okay, I'm going to show you what happens. In a unit circle, the measure of the angle in radians, or the radian measure of the angle, say it anyway, always comes out exactly the same as the length of the arc. So if the arc is 2 feet, the angle is 2 radians. If the arc is 6 feet, the angle is 6 radians. The arc is 4.2 feet, the angle is 4.2 radians. The arc and the angle are always exactly the same on a unit circle. So on a unit circle, the angle measured in radians, not degrees, the angle measured in radians is exactly the same as the length of the arc. Always match. So, I'll give people a second to copy that. The so part you don't need to write. It's just explaining what I'm about to go through with you. So just go through it with me and you'll be fine. What's the angle that goes all the way around the circle in degrees? 360. So we know that. So I have degrees, radians. What I'm trying to do is figure out my 1 foot, 12 inches. I'm trying to figure out a fact to start with. And once I have that, I can use it to do other things. All right. There's a unit circle. What's the radius in a unit circle again? 1. Have that join his friends. All right. So, 1. So I've got a unit circle. I know the angle that goes all the way around is 360 degrees. What I don't know is what it is in radians. But let's go back to that fact. The length of the arc is equal to the measure of the angle in radians that goes all the way around. So I can figure out something else. If I can find the length of that arc that I just drew in red, that goes all the way around the circle, whatever it is, it's exactly the same as the angle that goes all the way around in radians. So we're going to find the length of the arc. All right? So let's see if we can find it. That arc is really so big that it takes up the whole circle. What do you call an arc that takes up the whole circle? You can still call it an arc, but they have a better name for it. It's the circumference. So if we can find the circumference of that circle, that's how many radians it takes to go all the way around, because the arc and the angle are the same in this circle. So the formula for circumference is 2 pi r. What's my radius in this circle? 1. So the circumference of the circle is 2 pi times 1, or 2 pi. Now, that's an arc. So the number that I just found is exactly the same as how many radians it takes to go all the way around a circle. So how many radians does it take to go all the way around a circle? 2 pi. Yep. And there's my 1 foot equals 12 inches. That's my fact I can start with. 360 degrees equals 2 pi radians.
So when we do this, are we using the pi button, or are
Yes.
we pressing, or are we typing 3 button?
We're going to use the pi button.
Okay.
Yep. I'll hopefully get to that. So now we know 1 revolution equals 2 pi radians, or 360 degrees. Let's make it a little simpler. What could you divide each side by here? Yeah, we could divide each side by 2. And that's a little better. It's still not that great. It says pi radians equals 180 degrees. When you give someone a conversion, usually you give them a certain number in it to make it easy. What number is usually in a conversion? To make it simple. 1. Right? If you ask me how many hours in a day, I would say it's 24 hours in 1 day. Right? I wouldn't tell you that there's 48 hours in 2 days. That's a more complicated way of saying it. Just be simple. 1 day, 24 hours. 1 minute, 60 seconds. Things like that. So I have 2 choices. I can get a 1 on the left, or I can get a 1 on the right. If I put it on the left, that's going to convert between degrees and radians one way. If I put it on the right, that's going to convert between degrees and radians the other way. So let's start by getting it on the left. What would I have to divide both sides by to get a 1 on the left? That would be on the right. Pi. Let's divide each side by pi. Divide by pi. Pi's cancel. And what are you left with? What's pi divided by pi? 1. So 1 radian equals that many degrees. So if you want to know how many degrees in a radian, that's 180 divided by pi button. It's about 57 degrees roughly. Something like that. Now, that's a formula for 1 radian. What if I wanted to know 2 radians equals how many degrees? What could I multiply this side? What could I multiply that side by to make it 2 radians equals something. Multiply by 2. But if I do it on the left, I have to do it on the right. Now you have a formula for 2 radians. 2 radians equals, and you could do out the calculation. What if you wanted to know 5 radians? Multiply by 5. I want you to notice what's not changing. What's in that box? It's always a 180 over a pi times something. If you want to know 5, it's times 5. If you want to know 12, it's times 12. If you want to know 30, it's times 30. But you always take what you want to know times 180, divide by pi. So that's how you convert. I got it on the next page. That's the next one we're going to do. So if you want to convert radians to degrees, it's always times 180, divide by pi. That's the 2 steps. So times 180, divide by pi. So that's radians to degrees. And then either next to it or below it, you want to put another thing, you're going to have degrees to radians. It's basically going to be the opposite. Okay, let me go back here. Where did I have it? Okay, so we chose to get the one on the left. Well, let's take the same formula. Pi radians equals 180 degrees. How would I get the one on the right? Divide by 180. Just 180, no unit with it at all. Just the number 180. So that leaves the little degree symbol on the right-hand side. And 180 divided by 180 is 1. 1 degree equals pi over 180 radians. So now I've got a formula for 1 degree. 1 degree equals that many radians. What could I multiply each side by if I wanted a formula for 2 degrees? Multiply by 2. Now the right-hand side says 2 degrees equals, and now I would do out that calculation, and that would be my answer. What's going to stay the same every time is what's in the box. You're always going to take what you're trying to convert, you're going to multiply by pi, and divide by 180. That's how you convert from degrees to radians. Multiply by pi, divide by 180. Now, they're very similar. Right? Very easy to mix them up. One's multiply by 180, divide by pi. The other one's just kind of switched around. So I'm going to show you a way you can remember these, and you don't even have to really memorize which one is which. The only thing you have to remember, 2 things. When I say degrees, the number I always want you to connect in your head with degrees is 180. So degrees, think 180. Degrees, think 180. When I say radians, I always want you to think of pi. So radians, think pi. Radians, pi. You can remember those 2 things. That's all you need to remember. Degrees, 180. Radians, pi. And I'll show you a couple examples of converting between degrees and radians. Okay, so it says to convert 30 degrees to radians. I have 2 choices. It's always one of these 2 fractions, pi over 180 or 180 over pi. I've got to figure out which way. Well, think of 30 as part of a fraction. You could put it over 1 if you wanted. So you've got degrees in the top. You're trying to convert to radians. So you want degrees to cancel out. If it's in the top of the fraction on the left, where would it go in the other fraction to cancel out? It would go in the bottom, which means radians would have to go in the top. Now degrees would cancel. Degrees in the top, degrees on the bottom. Now we just figure out which number goes where. What's the number I said to always think of when you think degrees? 180. 180. And the number you always think of with radians? Pi. Degrees cancels. 30 goes into itself once. 30 goes into 186 times, and you pretty much leave your answer like that. You don't even press the pi button for this one. 1 times pi is pi. 1 times 6 is 6. And that's your answer, pi over 6. Now, if you look at what I circled, what do you think? Some people might think I forgot to write. But I didn't forget to write anything there. The what? Exactly. There is nothing labeled there. Just like here. If you don't see a label, it's always assumed to be radians. So you got to kind of get used to not seeing RAD. You're not going to see RAD written on any problems on the test or in the homework. All right. How do you know it's a radian then? Well, if it doesn't have the little circle next to it, then you know it's a radian. All right. Let's just try to do one of each. So let's do another degree problem. This time it's different. They said round the answer. So this is when Jake and Matt asked, do you use the pi button? Yes, we're going to use the pi button now. Don't use the pi button unless they tell you to round. Okay, so I want to cancel degrees out. Where would it go? Top or bottom? Bottom. Means radians is going to go in the top. I'm not going to write RAD this time. What number goes in the bottom? Number in the top? Pi. And now I know I can reduce 50 and 180. I could reduce by 10. But there's really no point because we're just going to type it in. So 500 times pi and divide by 180. Calculator will handle all the order of operations fine there. Okay, so 8.73 radians. So that's how you change degrees to radians. Let's try, we'll quickly try one going the other way, but it's kind of the same thing. Okay. Convert to degrees. Again, if you want to pretend RAD is written in the top, you can. But you're not going to see it. But I'll do it on the first one so you can see it. We've got radians in the top. We're trying to convert to degrees. So we want radians to disappear. Where would radians go this time to disappear? Bottom. You always put the one in the bottom you want to get rid of. Which means what unit is in the top? Degrees. That's the 180. And what's the number with radians? Now, look what cancels here. Pi, pi, radians, radians, and 2 goes into 180 how many times? 90. So all you're left with is 3 times 90. Done. What's 3 times 90?
270.
270? Do I need to put the little circle on it? Yes. If I leave it like that, that's 270 what? That's radians. I want degrees. And the last one, it's the same idea, except now you're actually going to round it. Okay, trying to get rid of radians. Where do you put the thing you want to make disappear? Put it in the bottom. I'm not going to write RAD this time. 180 is in the top. And now just type it in. So 3 times 180 is 540. Divided by pi. That's the correct answer. If you did 3.14, look what you get. You get 171.97 versus 8.9. That's off by almost, that's off by quite a bit. All right, so stick with the pi button. So the answer here should be 0.89. Questions on that? All right, so homework tonight, just lots of little questions, like finding coterminal angles, converting between degrees and radians. It probably won't take you more than like 15 minutes. It's very quick. So it's 323, 1 through 3, 7, 9, 11, 12, 15, 24 to 26, 30, and then 35 to 37, 41 to 43, 47, and 51 to 53. Again, looks like a lot of problems, but they're all very, very, very quick. Okay, so we'll finish up section 6.1